Hi, my name is Yomi, Tutor Yomi, and today we're looking at Laplace Transform. Okay, for those who probably are in the engineering field, like myself, you know that Laplace Transform is not something new to you. Either you graduated from engineering, any of the engineering, you probably did Laplace Transform. I'm correct. And if you're in 300 level, 400 level, even 500 level, you know that Laplace transform is something that you must have done either in a particular session, semester, as a case may be. And that's what we're looking at very quickly. When we talk about Laplace transfer, actually, it's something that in engineering or in physics, it is used to solve what we call differential equation and system that has varying time condition. You might want to know, are there applications of Laplace transform? Of course, there are. There are. I know those in electrical know that there are a lot of advantages and applications of Laplace transform. Yeah, Laplace transform can be used in what we call ventilation in heating, even your air conditioning system modeling. It can be used. Yes, it can be used in the designing of what we call your electrical circuits. It also can be used. In fact, there's a course in electrical field called circuit theory. Circuit theory. So those in electrical, they know that the circuit theory is something that is not a joke at all. Well, that's not what I study. I study chemical engineering. So, but we're looking at Laplace transform. Okay. Now we know that the Laplace transform, let me call it, of f of t is equals to this. Okay. So that you can call this one an input function, and then I can call this an output function. So I can have that the f of x can there be from infinity to this, so that I have my xt f of t dt. So here you have the varying time. I define it, if you remember what I said about the varying time. Okay, so we have the complex parts, and this is the f of t that was defined in terms of this. So you have this, and whenever you're given question, your f of t, you can be varying it. You can be varying your f of t. So your f of t can be 1. So if your f of t is 1, then you have infinity to 0, and then you have this, so that you have just 1. If you multiply, that's 1 dt. And so that you can have something like the f of t 0 and the ext dt. And you know, to integrate this one is very simple, right? How do I know it's very simple? So long you can integrate something like this in mathematics. So if you can integrate this, you can integrate it. So to integrate it, how do you integrate this normally? To integrate it, this is 1 over 5 and then 5x plus c. Okay? You remember the 5 comes down the reciprocal of whatever you have here. You have it here, and then you have this back. Okay, so this is very simple. If you use what we call substitution of integration, you can do this. Very simple. So apply that here. So in the place of x, the x is the 5, because the x here is a constant. The x there here is a variable. So the t here too is the variable. So if you are to integrate this one now, integrating that, you are going to have, what do you think you have? You will have minus 1 over x, and then a raised to power what? Xt. So that you now have a constant divided by 0. Am I correct? Very simple. So from here, you can put your x outside, and then you can do this. So what do? You have x multiplied by your infinity minus what? X multiply by 0. So because it's a definite integral expression, and so being a definite integral expression, that's why I'm doing it that way. Okay, so let me wipe the board somewhere there. So what do you have? So you have minus 1 over x. Now this is infinity, right? Okay. Imagine a value called infinity, such a big amount, gigantic value, right? If you multiply it by x, obviously this x will be swallowed up here. So you will have exponential raised to power minus infinity. And automatically, as you do all of that, you are going to have 1 all over because of this. So it's going to be leading to what we call 0. So take note of that. This place, the entire expression here will lead to 0. You can confirm it yourself. And then when you multiply this by this, you will have 0. And infinity divide, exponential divided by 0, you have 1. And that gives you 1 over a. So the Laplace of what? The Laplace of, what was the Laplace we saw? When f of t is equals to 1. See what we got? We got 1 over x. So the Laplace of this is this. Do you understand that now? So let's test another thing. Let's test that it is this way. Okay, so suppose you are given f of t, that's question 2. Suppose f of t is equals to this lambda t. So it means that my f of x is equals to this, is equals to this, so that you have xt, and then you have lambda, what? dt. Very simple. Okay, how do I do this? Of course, this is common, right? So what do you do? Apply your law of indices. So if you apply your law of indices, what do you have now? T is common, so T can go outside. So I can have x minus T, okay, T here. That is, if you open this bracket, you have this, you have this. Okay, okay, no, this is lambda, excuse me. This is lambda. So we have dt. If you open this up, you still have it back. So there's no issue at all. Look at what I'm saying. If you open this thing up, you have minus. If you open this thing up with this, you have this. So you have not done anything wrong. So from here, we can recall again. What are we to recall? Remember, the variable is your t. So do not forget. Let me quickly remind you in case you don't understand. If you have something like this in mathematics, let's say you have ln x, let me use another value now, 2x dx. You can say let u equals to 2x, and so you have du dx equals to 2x, equals to 2 rather, and then you make dx, it becomes du over 2. So come back to this place. In place of 2x, what do you put? You put what? You put u. And in place of dx, what do you put? Du over 2. So you have 1 over 2 equals to du raised to power 2 du. So we have 1 over 2. By the time you integrate this, it becomes the same thing. So you have the, by the time you put the u back, you have 1 over 2, 2x. Exactly the same thing. So applying that to this, so what are we going to have? That means we have 1 over x lambda, yes, 1 over x lambda, e minus x xt, infinity 0. Do you understand that? Look at it. This thing came down, the constant. Then you have it back, just as you have it here. Very simple. Very simple. So what's the next thing? Now it is to work on this. So I have my 1 over x lambda outside, and then I'll put this here in place of this. I'll put here. So I'll have E x lambda multiplied by infinity minus I have x lambda multiplied by 0. So I have minus 1 over xa. Remember again what we said. Take this to be a constant value, or whatever value you may think it to be. Multiply by infinity gives you an infinity. And so when you have exponential raised to power minus infinity, that gives you 0. When you multiply this by 0, it gives you 0. And so you have that. So this gives you 1 minus lambda, so that you have 0 minus 1. And finally, we have 1 over 1 minus xa, lambda rather. So it means that when you have a function of exponential lambda, the Laplace is x this. And this lambda can be a. So it means that in another question, it can be given like this as a raised to power 8c. So this a therefore comes here. It can be any alphabet. If it's b, it is b that will be here. It can be anything, you put it there. I'm sure that's very clear. So watch out on my page as I come up with different solution henceforth on an engineering field. And I'll be coming up with different courses and different fields of learning. But watch out particularly for engineering mathematics. Bye.